Okay, so after a couple of audio tests, I'll have to edit it out and make this louder, but this should be my first video. And yeah, I'm not sure if I'm going to edit this out as well. So what am I trying to do here? So I have a, so let's see. So there's this book, Topology, right? And my goal is to finish this completely by the end of summer, right? So to do that, I've tried to hold myself accountable by essentially uploading, all the solutions. My goal is ultimately to write down all the solutions and upload this to YouTube, right? And yeah, ultimately, I don't particularly care who watches these videos. It's mostly think of it as like a vlog, and I'll try. So I'll pretend as if I'm teaching, but it's going to be mostly just yeah, just me writing down answers or me writing down a convincing explanation for how to get to the solution, or maybe it's a hint, or yeah. And yeah, so I'm covering the entire book, so that will mean set theory. So I guess we can get started then. All right. So I am also going to assume that if anybody is watching this, they're going to just read the book, right? So if there's anything that the book covers that, so if the book is covering it, just writes about it, then talks about it, then I won't be I won't be saying anything. So any of that stuff. If I feel like I have something to add, then I'll add, right? And so I'll have a very short theory portion. Just I'll just maybe say the theorems, or if I feel like I can add something, then I'll add something. And I think they should be very short, and then I'll focus on solving the problems. Yeah. So that's my final goal. So let's see. What did I want to add? What did I want to add? So there's the definition of subsets, right? I'm assuming you've read it, so I'm just trying to help you understand it. And so the operations intersection and union, and one more I forgot. They're defined as so they're defined using logical operators. That's the key thing. So what does that mean? That means I'm going to write this instead of and, right? And this is or, this is implies, or this is implies, this is if and only if. I'll come to these two, and essentially these are just logical quantifiers. Did I miss one? Oh yeah, not. So all of these are just how we're defining set theoretic operations, right? So this corresponds to complement, which we'll get to, and yeah, there are many. For now, oh sorry, yeah. So in this case, we're using or. So this is how we're defining them, basically. Right. So I'm assuming you passed high school and have done something in logic, just any logic, just even the computer science truth table. So you should know the truth tables of OR, so, right? So you get 1, 1, 1, 1, 0, 1, 1, 0, 0, 0, and similarly for and not and so on. Yeah. So what else? Is it mirrored? Yes, mirrored. Oh well, should be fine. So I am seeing it mirrored, but I think the video flips it for you. So we'll see. Anyways, so this is how the union is defined, and for the intersection, it's defined using uh, and, right? So they're all pretty much logical operators. Uh, so when you write X not belongs to B, what it really means is not of X belongs to B, right? So they are still involved here. So if you're saying, let's say, X union B complement, first of all, what does a complement even mean, right? So it's always a relative complement. There's no such thing as the universal set. You'll study that you'll study that in set theory if you take a course. So because of that, so B complement just refers to some set which is clear from context. So it could be X or Y, whatever, and X minus B. And this is defined as X, X belongs to X, and and X does not belong to B. So it's short for this. So it's still a formula. Ultimately, all we're writing is a formula, and that turns out to be a set, right? Okay. So yeah. Then what I'd like to add is the notion of the null set, right? So if you have seen how set theory attacks uses the axioms to build the sets from scratch, you either have an axiom of the null set or you derive a null set through comprehension of the existence of the null set. So I'm not going into that. I think you can check out Kuhnen's book. He has two books. See the later one, I think, not the independent proof one. So that should help you if you really are interested. But ultimately, none of that is needed here, right? Since our goal is just topology, and with topology, I think you can solve some analysis books too. I think you should try if you're completely done with the book, you should try Baby Rudin if you haven't read it. So yeah, for the record of also this book doesn't seem to require any prerequisite besides high school math. So that's why I'm also trying it out myself. I have seen the book a bit, but from a point onwards, it's also going to be new form. So yes, adding about the null set. So the null set, it's a notation, right? So what does it represent? It represents a formula. So it says that for any set X, it's not going to have any of that guy's members, right? So for any set X, so these two symbols are essentially English abbreviations for all and there exists. Essentially treat them so. There is an actual meaning of the what a quantifier means, and and they're supposed to be written like in before and the order matters. But I'm going to treat them like words throughout the whole thing because well, some books do, and this is not too intense on the logic. So if you need to work with the quantifiers and you know work with the quantifiers and use them properly. So I suggest writing down the formula, but I essentially want to provide the intuition regarding the questions itself. And what else? So yeah, so for this is literally just for all, right? So for all x, and so the approach that the book goes with is that there are objects, sets, collections of sets. In reality, even the objects are themselves usually sets. That's how the whole foundation goes. So yeah, it doesn't truly matter, but if you've read the book and you can follow that there's no problem with it. But yeah, any background in set theory, there are some nuances to it. But the book is completely avoiding all such discussions for a very good reason. But all the set theoretic knowledge you need is in that chapter, and which we're starting to cover. Okay, so for any set x, um, x belongs to x implies x does not belongs to phi. So what does that mean? Phi has no members, right? That's what the null set truly means. And the axiom of the null set says that there exists such a set, right? But we're not doing that here. So yes, we're taking it to exist. Essentially, it's a property that so when two sets are disjoint, we're saying that intersection is the null set. So if we're assuming the existence of the null set, and from that we're using that. We're writing A intersection B or union B, no, union B is never phi, is equal to phi, which means, for all x belongs to A or x belongs to B, x does not belong to phi, right? This is from this. So it's true for all sets X. So it's obviously true for X and A and B, right? Yeah. So I wanted to add this a little bit. Shouldn't last too long. I don't want to spend too much time here. Contrapositive and converse should be fine. Uh, Accuracy true. So yeah, there's just so basically with P implies Q, there are two possible truth tables. So one is what? One is let's see, 1 1 1 0 0 1 0 0. So if it's so there are two tables, right? In that's what it's talking about basically, and this one is also true, right? True and false, false, and true implies false is false. False implies true is true. True, false. Yeah. So and this is true. So this is where it's different, right? And this is the case of accuracy true, and essentially we have two truth tables. This is the other interpretation of the conditional statement that we use, but this is used here as this and this. So you can write a tautology here. Tautology is basically mean the truth table lines up. So what does that mean? That means P implies Q and Q implies P if and only if P if and only if Q. So they're equivalent, right? So you can line up the truth tables and check all of the cases. This is basically P and Q, nothing to do with that, right? So that's all. And quantifier. So yeah, I think using for all and there exists as literal words works for the time being. That's why it's using it as a. So that's why it's literally writing for every and for there exists. And since you're almost everybody's used to symbols, you might as well just use these symbols, right? I will use them like sentences, and I hope there's no confusion. Yeah, ultimately, if you want to write a formal proof, you have to do a lot more than just study the book. So if you want to like write it so a computer could check this, that's the whole thing. But what it just says is for all x. Um, so for all x, so the x is arbitrary, it's just a variable, right? That's why he wrote the words for every instead of for all x because yeah. Oh, it's saying x in it. Yeah, all right. So typically in logic you're supposed to write it this way and then write x belongs to a implies something, and this is logically equivalent to for all x belongs to a something, the same something. So and you can replace this with the existential quantifier if you want, right? So that's how he's written it. And the reason he's written it like that is because, well, these are the only types of logical quantifiers we'll be using. Essentially, everything will be either a subset of the real line or subset of Rn or something like that. So because of that, we might as well just consider these, right? So a formal course in logic would have you use this notation, but we don't need to do that. So what does this mean? So what the book says is for all x in A, let's say we have a statement Q. This is equivalent to saying there exists not of this is equivalent to saying there exists x in A, not of Q, right? So check the truth tables out. Oh, right, check the truth tables out. So yeah, you'll have to actually like think about what exists means, right? Yeah, they have to read what this says. So there's no yeah, it doesn't work like truth tables, unfortunately. We'll have to see what the statement means and how quantifiers work. So quantifiers add a layer of complexity just good enough that we can do quite a few proofs with it. Like, yeah, almost all, basically all the proofs we use are using these quantifiers and this operators. So you can reduce them all down. Yeah, right. So what's next? Next is the De Morgan's laws and the distribution law, and that's we're going to check that in the exercises. And collections. Collections are all right. So I suggest you use this method to memorize De Morgan's laws. So I'm writing an arbitrary union, which is introduced later, or just whatever. Let's use an index. So A belongs to alpha. What do we use? U as A? Yeah. A is equal to intersection. Is that it? Yeah, intersection. A belongs to alpha x minus U. So this is, I think, a much better way to remember it, and that's what it's writing in English in the book. And these are just, you can flip these. That's all. So this is a better way of memorizing De Morgan's laws, and the distributive laws can be verified using the notion of subsets. So yeah, I will cover it in the exercises too. But to show that two sets are equal, you need to show that they're subsets both ways. And the definition of subsets is, well, okay, I'll just write it down. For all x in A, x belongs to B, pretty much. So it's actually like for all x belongs to A implies x belongs to B. But since this is the same thing as this, you can write it this way. And this is equivalent to saying A is a subset of B. And the reason we use subsets like this or this instead of the proper subset is because of the, this is quality, right? Okay. Hmm. Okay, so collections of sets. Yeah, that's just know what the definition of a power set is. So it's the power set of, there's a formula, it's a collection of all subsets of it. That's all you need to think about. Arbitrary union. So how is it? Hmm. So the reason we can do it is because of axiom of choice, but you don't need to think about that. I thought about it when I was studying it. So how do we think about it? So I guess the definition works out. So it happens to be a formula, right? You see that. So you can pretty much so by axiom of comprehension, you can actually write a set by a formula, and that's kind of what it's doing. So yeah, you don't need to think too hard about it. The definition works very well. So I'll try to use that definition, but yeah, essentially the definitions are equivalent. I don't think there should be a major problem. Worst case scenario, you'll get used to it. But ultimately, these are fundamental concepts, and we're just doing them without any arbitrary, difference in meaning. That's all. What else? Cartesian products. So yeah, if you take ordered pairs as a primitive concept, then you can define it using ordered pairs. A belongs to A, and B belongs to B. Same thing is equal to A cross B. That's one way of defining it. The other way is, you actually define this. So you can try proving that this, if this is equal to this, then and let's say C comma D is equal to A comma D, A comma B. So using this notation, then this happens if and only if C is equal to A and B is equal to D. You can try proving this. So you'll need to use some axiom of set theory. So this is a set theoretic exercise. I'll try to cover it, but essentially this is completely off topic. And yeah, so this is how you can define the Cartesian product. So it's another formula, as you can see, A belongs to A and B belongs to. So you just use this symbol and the logical operators. That's how you define any formula. And you're taking the set here. So the parameter, if you want to say it that way. All right. Yeah, so that's the theory portion, and I guess I'll try the exercises now.